Hello everyone. I am Teacher Chen from the Electronic Information Engineering Teaching and Research section of Wuzhou University, and welcome you to this mini lecture. Today we will study section 7.1 of chapter 7, the zero-state response of a system under complex exponential signal excitation. The main content of this lesson includes the zero-state response of a system under complex exponential signal e to the power of st excitation, and the procedure for solving the zero-state response of a continuous time system to an arbitrary signal. One of the basic tasks in system analysis is to obtain the system's response to any input excitation signal. Therefore, we can first represent any signal as a linear combination of elementary signals. In the complex frequency domain analysis method, the chosen elementary signal is the complex exponential signal e to the power of st. Therefore, we first discuss the zero-state response of the system when the input excitation is a complex exponential signal f of t equals e to the power of st. Since the zero-state response of a continuous time LTI system equals the convolution of the input excitation f of t with the system's unit impulse response h of t. The zero-state response of the system is given by the following formula. The result is the complex exponential signal e to the power of st multiplied by a factor h of s. That is, t e to the power of st equals e to the power of st times h of s. Here, the function h of s is defined. From the formula for h of s, we can see that h of s equals the Laplace transform of the system's unit impulse response h of t. Therefore, when a complex exponential signal e to the power of st is applied to an LTI system, the system's zero-state response is still a complex exponential signal of the same frequency, whose amplitude and phase are determined by the system function h of s. Observe the definition of the one-sided inverse Laplace transform as shown in the following formula. This formula shows that for any causal signal f of t, if its one-sided Laplace transform f of s exists, it can be decomposed into a linear combination of complex exponential signals e to the power of st. Furthermore, since the system is a linear time-invariant system, we can deduce that the zero-state response of the system to an arbitrary signal f of t is yf of t equals tf of t. At this point, if the one-sided Laplace transform of f of t exists, the signal f of t can be expressed as a linear combination of complex exponential signals e to the power of st, as shown in the second line formula. Combining the homogeneity and integration properties of linear time-invariant systems with the zero-state response under complex exponential excitation. That is, when a complex exponential signal e to the power of st is applied to an LTI system, the zero-state response equals e to the power of st multiplied by the system function h of s. We can finally derive the expression for the zero-state response yf of t of the system to an arbitrary signal f of t, as shown in the following formula. The relationship inside the box is the S-domain expression of the zero-state response yf of s equals the product of f of s and the system function h of s. In the time domain analysis method, the zero-state response of the system equals the convolution of the input signal with the unit impulse response. In the complex frequency domain analysis method, the complex frequency spectrum of the zero-state response equals the product of the complex frequency spectrum of the excitation signal and the system function. This is consistent with the time domain convolution property of the one-sided Laplace transform. Therefore, the system function h of s can also be expressed as the ratio of the Laplace transform of the system's zero-state response to the Laplace transform of the input excitation. Let us look at an example. Given that the impulse response of an LTI system is h of t equals e to the power of negative 5t times u of t, find the expression of the system function h of s and compute the system's zero-state response yf of t to the signal. F of t equals e to the power of negative 2t times u of t. First, taking the one-sided Laplace transform of the impulse response h of t gives the system function h of s equals 1 over s plus 5, with the region of convergence are e of s greater than negative 5. Similarly, taking the one-sided Laplace transform of the input signal f of t gives f of s equals 1 over s plus 2, with the region of convergence are e of s greater than negative 2. Then, using the formula that the complex frequency spectrum of the zero-state response equals the product of the complex frequency spectrum of the excitation signal and the system function, we obtain yf of s as shown in the following formula, with the region of convergence are e of s greater than negative 2. Finally, taking the inverse Laplace transform of yf of s yields the time domain expression of the zero-state response, yf of t, as shown in the result. This is the complete procedure for solving the zero-state response of a continuous time system to an arbitrary signal. Please master it proficiently. Finally, please reflect on today's lesson and complete the following exercises, which are designed to consolidate the knowledge points learned today and further deepen your understanding. This concludes today's class. See you in the next lesson.